Hello, everybody. Today we are presenting some new results, namely how to integrate a new control method called B control to the L1 adaptive controller in order to get improved performances. The new results we have in robust control are quite innovative in the sense that they optimize both frequency response and time response. They allow to optimize both of them at the same time. They use also graphical intuitive methods so they can be tuned very easily. And we're going to see how to integrate this new B control to L1 control to have a new method of control called BL1. So first we'll recall a few performance objectives and introduce the B controller, then the adaptive control schemes, namely the traditional MRAC, the L1 controller, and our new proposal. Let's consider this feedback system, a unity feedback system, where PFS is a plant and CFS is a compensator. And we have here the perturbances D1, D2, and D3, external perturbances, input plant perturbances, sensor noise. And we have here all the transmissions. And in fact, we have 4 transmissions between Y, U, and R, and the 3 and the inputs. Okay. Our aim naturally is going to be to make Y to R as close to 1 as possible and minimize the transmission between Y and D1, Y D2, Y D3. What's new about this B control? Basically, it's based on sensitivity considerations. We're going to suggest, to propose some sensitivity constraints in low frequencies and over all frequencies. We aim to have a closed loop as close to 1 as possible, a phase margin to 67 degrees, as Astron proposes. And our aim also will be to avoid the saturation to input. That means we want to limit the amplitude of U of S. And we want actually to do that with a reasonable gain for the compensator. The unity feedback system is as such, as you can see, sensitivity S and closed loop transmission T are related by T plus S equals 1. It can be verified very easily. But ideally, we would like to have T equals 1, which means S equals 0. But it's impossible to have T equals 1 at all frequencies, because at high frequencies, for causality reason, T has to be strictly proper, therefore T of infinity at high frequencies should be 0. So it's impossible to get the ideal T at all frequencies. So what we're going to do is the following. We're going to assume that S equals as close to 0 as possible at low frequency, that means T equals 1, and S going to 1 at high frequency, which means that T equals 0. But at the same time, we're going to limit this overshoot here, because this overshoot always exists. We'll show why. If we take the log sensitivity theorem, you can see here that one way of improving sensitivity, this is a sensitivity curve, is to increase the gain C, because 1 over 1 plus PC goes to 0 when C increases. But when we increase C, the sensitivity decreases, but at the same time, this area, the green area, increasing, because this area and this area are basically the same. So how to do it? What I'm suggesting simply is to avoid here a high peak, because if there's a resonance frequency, it's a big problem. And we're going simply to have a slow M and go on higher frequency. This area should be on higher frequencies. Today it's possible because 2 factors allow that. Number one, that today most of the sensors are high resolution, high bandwidth, so it's not a problem. DSP speed can be increased easily, so it's possible to do that. Another property of this B control is a quasi-linear property, which means that if I'm increasing the gain, I'm stabilizing more the system, and the time response improve. It's counterintuitive, but I'll explain in a moment why. And as I said before, there's an interactive graphical program that adjusts the compensator parameters. Recall, this is the M circles, which simply say that the modulus of the closed loop is equal to M for value of M, and ideally it's 1. That means in a Nyquist plane, we should have the Nyquist locus stick as much as possible to this real value of -1, which corresponds to t equals 1. That means to the ideal. It won't be possible at all frequencies, but we try to match it at most frequencies. Now, sensitivity has to be small. How do we know? How can we measure the sensitivity? We have what we call sensitivity circles. That means if my Nyquist is outside this green circle of radius 1 over epsilon centered at -1 here, then the sensitivity is smaller than epsilon. And if the Nyquist is external to this blue circle of radius 1 over ms, sensitivity is smaller than ms. So the intuitive idea is to have a Nyquist which is external to the green circle at low frequencies, and at all frequencies should not touch this circle or should not penetrate this circle. Now, what is a quasi-linear property? Normally, this is an Nichols plane. If I'm increasing the gain here, you can see I'm increasing the gain, and what happens? The system starts to oscillate, and eventually, when I'm getting to the critical point, that means -1, or if you want 180 degrees at 0 dB, the system implodes. So to avoid that, we keep changing the frequency of the system and match the gain, relate the gain. Gain is frequency dependent. That means the poles of my system and the gain of my compensator are related. Doing so, if I'm increasing the gain, in fact, this curve keeps always contouring, going around the critical point. The advantage is that you can see here, when I'm increasing the gain, what's happened? I'm getting closer to the ideal time response. This has been tried on a levitation system. This is YouTube.
This new algorithm takes advantage of new sensors, which are much more precise, have higher resolution, higher bandwidth, as well as digital signal processing units, which work much faster. Our compensator is shown here in this diagram. We invert the invertible parts of the compensator and add some corrections, as well as 3 filters. J1 acts on low frequencies, and J3 acts on high frequencies. And those 2 filters guarantee the realizability, the stability, the robustness of the system, while G2 of S acts mainly on the time response, reducing the settling time and the rise time, without affecting really robustness margins. That's the strength of the algorithm as it is now. We apply now a new control algorithm on the levitation system, and we're going to give some step inputs and check how the ball is reacting on the vertical plane. And as you can see, there's almost no oscillation when we go from one step to the other. If we look at the time response and zoom on it, we can see that there's almost no overshoot, no static error, and in less than 60 milliseconds, we get a nice response. Note also that the rise time and the settling time are equal. If we do compare our compensator to a PID compensator, which has been optimized after many trials, we observe the following. Number one, the overshoot is quite important. Static error is small, but the settling time is quite big, 650 milliseconds. Therefore, our compensator performs much better.
We continue. Multivariable case, there's an extension of the multivariable case, and this has been applied to quadropter. And what you can see here is the PID controller that the manufacturer proposes. The whole idea is to try to stay as close as possible to the vertical pole. So you can see it can swings on the right and left. Okay, let's go now to the second one, to the solution we propose. You see here trying to get as close as possible to the pole. Let's start. We continue. Those are the horizontal swings measured using B is the B controller, H2 is the green one, H infinity is the blue one. As you can see, with our controller, we get better results. Now to L1 adaptive control. Adaptive control tries simply to minimize the difference between a reference model and the plant, the actual plant. So there's two methods, classical methods called model reference adaptive control, direct and indirect, and you have the L1 improvement and what you're suggesting. In the MRAC, as you can see, we have a reference model, and the difference between the reference model and the actual plant, the difference is fed back in a feedback loop, which typically is an MIT gain, and we're getting an improved performance. In this case, we have a perturbed system, but we have a state observer and have a system. The only problem with this two is that when you increase the gain, the phase margin is reduced. Now, L1 adaptive control add a special filter. This filter has the advantage of filtering the high frequencies perturbations, so you don't have to adapt to very high frequencies, and that improves completely the performance, because C of S is a low pass filter, and this C of S is going to affect mostly the internal responses, but won't affect the general transfer functions. And on top of that, when we increase the gain, we increase the phase margin, which is exactly what was the problem with the MRAC systems. Now, BL1 trying to integrate L1 adaptive control and the B control. To do that, we have here a system. This is the L1 controller, and I'm going to consider this as a plant, and this is my compensator. As you can see here, this is one scheme possible. There's many architecture possible, but with this architecture, what we get something like that. First of all, input to output relationship. As you can see here, the rise time is very small. With higher gain, we get improved time response, definitely. Again, this time response we have gotten can further be improved, but I won't get into it right now. This is the response to noise with L1, and this is the response to noise with BL1. So integrating the two has advantages. There's alternative methods, but I'm taking the plant and I'm having here my B controller, and I'm trying to, again, minimize the difference between those two schemes. Here, another possible, instead of comparing to a reference model, I compare it to the ideal plant I can really build with the B controller. And this difference is fed back. And again, this is to be explored. What we get here using BL1, adjusting the elements, we get some very good response. Finally, what we have now are the transmission between output, input plant, and various points in the feedback loop with the input and the external and internal perturbations, which we call the gang of six. And doing that, we have some, as you can see here, C of S influences the transmissions to noise, to output noise, and to input noise, while the output here doesn't change. Right. What we have here are the transmissions between output and noise, input noise between output and output noise. What you see here is simply those transmissions are here, they're normalized, and my whole idea is to adjust the parameters of the filters so that we get all those transmissions within the circle. You see here? Getting them in the circle. When they're all smaller than 1, that means we have attenuated them. So this interactive method is very powerful. And with that, I finish. Thank you very much.